Hello everyone, my name is Sanskar Bhangdiya. I'm roll number BT21CME024. My topic is titrators and I'll be mainly focusing on iodometric titration. It is guided by Mahesh Verma sir. It is our IIT assignment. So let's proceed. So first of all, what are titrators? So titrators are the essential tools in analytical chemistry, particularly in uh, quantitative analysis. These are automated instruments designed to perform titration, a common method for determining the concentration of an unknown substance. So there are titrators work by precisely controlling the addition of the solution with known concentration to the solution with an unknown concentration, which is of analyte. So there are different types of titrators. So as we have seen, so we have potentiometric titrators, Carl Fischer titrators, colorimetric titrators, and various types of different titrators. Acid based titrators are also there. So what is the general purpose of using titrator? So titrators are widely used in various fields such as pharmaceuticals, food science, environmental monitoring, and industrial quality control. They provide accurate, precise measurement and enabling scientists and an analyst to control chemical processes and ensure product quality. So let's see the importance of titrator in quantitative analysis. So basically there are three things which we look for. First thing is concentration determination, then purity assessment, and the third one is reaction stoichiometry. As we know, titrators play a vital role in quantitative analysis. It involves determining the amounts of specific substances in different samples. The accuracy and the precision of titrators enable scientists to obtain reliable data for various applications. So these are the three applications as I spoke before: concentration determination, purity assessment, and reaction stoichiometry. By using different titrators, analysts can determine the exact amount of components in complex mixture, ensuring the product quality and regulatory compliance. Then now we are deep diving into the redox titration. As I said, first we'll be looking the titrators and we will be looking in particularly the iodometric titrator. So before that, we should know what is redox titration. So redox titration is a type of titration which involves redox reaction. Redox means oxidation and reduction. Name itself suggests reduction and oxidation basically. So oxidation and reduction reactions. In this reaction, electrons are transferred between the titrant and the analyte. One species is oxidized, basically it loses the electrons, and the other is reduced, basically it gains the electrons. It's quite simple. One which loses the electron is oxidation, and one which gains the electrons is reduction. So there are three steps. First of all, redox titration principle. What is the basic principle behind the redox titration? The so basic principle is that a titrant that reacts with the analyte is known as is known to us in particular stoichiometric ratio. The equivalence point of the titration is reached when the amount of titrant added is chemically equivalent to the amount of analyte present. Now the application in chemistry, redox titration are widely used in chemistry for various purposes. Laboratory testing, redox titration are also used in laboratory testing for determining the concentration of substances in various samples such as water, food, and pharmaceutical products. Now let's deep dive into iodometric titration. First of all, I want to give a brief intro that iodometric and iodometric titration both are different. In iodometric titration, the I2 ion, basically the reduction of I2 ion takes place in which I2 ions turns to iodide. And in iodometric titration, which we are going to learn here, the I2 minus ions, basically iodide ions, turn to I2. So basically here we are losing the electrons, which is basically the oxidation. In iodometric titration there's a reduction, and in iodometric titration there's the oxidation, the static process. So in iodometric titration is a specifically type of redox reaction titration that employs iodine as the titrant. It is widely used technique in analytical chemistry for determining the concentration of various analytes, particularly that can be oxidized by iodine. So let's go in the definition part. In iodometric titration, the analyte is not directly titrated with the iodine. Instead, a known excess of iodide ions, usually they are I2 minus, is added to the analyte solution. The analyte reacts with the iodine ions, resulting in the formation of iodine. So the general purpose, it is the liberated iodine in the titrated with a standard solution of sodium thiosulfate, which is Na2SO3, which reduces the iodine back to iodide ions. The amount of thiosulfate used to reach the end point of the titration is directly proportional to the amount of analyte present. Now, where are the common use cases of iodometric titration? So basically there are different applications we can see. It is generally used in determination of copper concentration, analysis of oxidizing agents like KMnO4, K2Cr2O7, then measurement of vitamin C, ascorbic acid content, quality control in food and pharmaceutical industries, environmental monitoring of pollutants. Basically, its ability to measure the concentration of various analytes makes iodometric titration an essential tool in chemical analysis and quality control. Now, what are the different, what we say, the setup of this? So basically, as we have already done in our OCS lab in the second year, every one of us have gone through the titrations. So the basic setup is like normal titration setup. Basically, we'll be having a burette, then a flask, then a stirrer, and an indicator. Indicator can be methylene orange or a starch solution, or it can be phenolphthalein. So where we get the end point and we are reaching to our conclusions. So basically in burette, a graduated glass tube used to dispense the titrant, which is sodium thiosulfate precisely. In a flask, a container where the analyte solution is placed and where the titration reaction occurs. Stirrer, basically there's simple stirring is all time going on. An indicator, a substance, usually starch, added to the analyte solution to indicate the end point of the reaction. Starch reacts with the iodine to form a blue-black complex which disappears when all the iodine is consumed. We'll be looking a video for this. Basically first we'll go through the working principle of iodometric titration. So basically there are three steps. First, it is a reaction initiation. Iodide ions, which are I- ions, are added to analyte solution and the analyte reacts with iodine, releasing I2. This reaction involves the oxidation of analyte and the reduction of iodide ions. The step 2 is titration with thiosulfate. The liberated iodine is then titrated with a standard solution of sodium thiosulfate, which reduces the iodine back to iodide ions. The endpoint of the titration is reached when all the iodine is consumed and the solution turns colorless. The amount of thiosulfate used is directly proportional to the amount of analyte present. Then the last part is the starch indicator. The starch is added to the analyte solution as an indicator to visually detect the endpoint. When the iodine is present, a blue-black complex forms between iodine and starch. As the titration proceeds, the iodine is consumed, the blue-black color disappears, indicating the end point. Now here we have considered example of copper ions, where copper is reacting with the iodide ions, which in turning it to CuI plus I2, then titration with thiosulfate occurring, and here we'll be getting a I2. So Na2SO3 when react with I2, which is iodine ions, turns to NaI and Na2SO4O6. So basically this is the typical example where the copper is used. Now we'll see the detailed working mechanism. Basically there are two steps. First is preparation and addition of reagents. First, a known weight of a sample containing the analyte is dissolved in a suitable solvent. Excess potassium iodide Ki is added to the analyte solution and the reaction is allowed to proceed until all the analyte has reacted with iodine ions. Liberated iodine is then titrated with a standard solution of sodium thiosulfate, which is Na2S2O3, which is added from a burette. Starch solution is added as an indicator near the endpoint of titration. Step 2 is reaction continuation and endpoint detection. As the thiosulfate solution is added, the iodine is reduced to iodine ions, okay, and then the blue black color forms. So let's see the example for this. So we have an example here with us, so let's look into it. Yeah, so this video shows us about this redox reaction. So let's listen what he speaks. There is the reaction between iodine.
So in this first video we've got some aqueous iodine in this conical flask at the bottom, sodium thiosulfate in the burette. I'm going to add the sodium thiosulfate from the burette and just give a swirl, and you can see that the colour is gradually fading.
basically this is a reaction between iodine and sodium thiosulfate.
See now, it's going. You can see.
Now we can see
In this next demonstration.
end point. Demo 2, the detection of the endpoint of the starch using.
In this next demonstration, we've got still sodium thiosulfate in the burette and aqueous iodine in the conical flask beneath. Now the previous one, where we added the thiosulfate directly to the iodine, gave a gradual loss of the brown colour. That's not very good for titration. We want a sharp colour change. So we're going to use starch as an indicator. We don't want to add that initially because it will bind too strongly to the iodine and give us inaccurate results. So what we do is we add some of the thiosulfate until the colour has faded. So I'm just going to be cautious about how I add that. You can see the colour is fading. It's still a brownish colour. We're aiming for a sort of pale straw colour. So a sort of pale yellow colour. I'm almost there. I just don't want to overshoot this. It's very tempting to add this too quickly and then we overshoot. There's something close to this. Yeah, I think just another drop or two more. There we go. So now we're ready for just one more drop. Yeah. The starch won't go a blue-black colour. We had about a centimetre cubed of starch from a pipette and we've still got plenty. So now what I'm going to do is just set the burette to add this dropwise. Now if you were doing this in real titration mode, you'd add one drop at a time, but I want to just show you what the colour change looks like by adding dropwise. You see still the blue-black colour, and you should be able to see just in one drop it's gone to completely colourless.
Now demo 3, producing iodine by oxidation iodide using I3.
So that second titration with starch was excellent to work out the concentration of iodine. But what we can do to broaden the applicability is to actually generate a stoichiometric quantity of iodine from another chemical. And in this case we've got Fe3+, which we can conveniently analyse the concentration of by first reducing it to iodine. So if we add some potassium iodide, it doesn't matter exactly how much, you just need to use an excess. You can see that we've got a nice brown iodine solution. So if I just lower the burette now, we're ready to titrate this. We're going to add it fairly slowly because I don't want to overshoot that end point. Once we get to the pale straw colour, we're going to add the starch. Speed up a little, but don't want to overshoot. Just adding little drops. Okay. We're very, very close now. You can see the colour. It could just be one more drop. There we go.
Now we see the next slide. So yeah. So what are the applications of iodometric titration? So it is used in chemical analysis, environmental testing and biological assays. In chemical analysis, iodometric titration finds white space use in the chemical analysis, which is basically determining the concentration of oxidizing agents. For example, it is employed to quantify the amount of hydrogen peroxide in a solution. Then as a part of environmental testing, it helps in determining the levels of pollutants such as ozone and chlorine in water samples, contributing to the monitoring of water quality. Then biological assays, it is used to measure the activity of enzymes such as catalase, which catalyze the decomposition of hydrogen peroxide. Now advantages of iodometric titration, it is very highly accurate. We get a proper visual endpoint and wide applicability. We can use it various fields. So yeah, it offers a high degree of accuracy in determining the concentration of analytes, and due to the precise stoichiometry of the reaction involved. Then as we talk about the visual endpoint of the iodometric titration is readily observable thanks to the characteristic color change of the starch indicator upon the addition of the iodine. We have seen this in video, how the color change, and it is very sharp. We have used the starch solution there, starch indicator. And the last, wide applicability. The versatile techniques is applicable to a wide range of analytes, including both inorganic and organic substances, making it a valuable tool in various analytical fields. Disadvantage of iodometric titration. Sensitivity to air and light and air. So iodine solutions are sensitive to light and air, which can lead to decomposition and inaccurate results. So we have to store it properly and need for fresh solution, because when we have to reach to a proper conclusion, we have to do this experiment many times to get a proper average readings that it is correct or wrong. So solution used in iodometric titration must be freshly prepared to avoid decomposition of iodine, which can compromise the accuracy of the results. Again, the operator skill, yeah, the one who is handling this need to be very trained one to get the proper result. Then important precautions in titration: handling of reagents. The reagent handling is very must. Light protection, because iodine solutions in the store iodine solution in dark or amber colored bottles to minimize the decomposition due to the exposure to light. This is particularly important for long term storage. Endpoint detection: the endpoint of an iodometric titration is often marked by appearance of a blue black color with the addition of starch indicator. Pay close attention to the color change to ensure accurate results. So there's a comparison with other redox titrations. Here we have iodometric titration, and here we have permagometry. So in here the indicator uses starch. Here KMNO4, the endpoint blue black, as we seen also a video, and here the endpoint is pink. Strength is highly accurate, visual endpoint, and versatility. It is self-indicating, wide applicability, and where the weakness about both of them is sensitivity to air, as we have read already, and about this can be affected by impurities endpoint and be subjective. So advanced application in the industry, quality control in pharmaceuticals, then food testing and precision in testing. Then lastly, there's a limitation of iodometric titrators. Sensitivity of starch. As we have seen, starch, the commonly used indicator in iodometric titration, is sensitive to temperature and other factors, which can surely affect the accuracy of endpoint. Then sample compatibility: not all the samples are compatible with the iodine titration. Certain substances may interfere with the reaction and or react with the iodine in unwanted ways. Solution stabilities: iodine solutions can be decomposed over time, leading to inaccuracies in titration. The stability of iodine is influenced by temperature, light, and the presence of impurities. Safety and environmental consideration: there should be proper handling precautions, all gloves and all should be done, proper disposal of the solutions to be done, testing solutions, and the storage. As we state, direct sunlight can't be given to the iodine solution, so it should be kept in dark, and proper labeling should be done. Conclusion: iodometric titration is a powerful analytical technique with a wide applications: chemistry, environmental science, and biology. It offers advantages like high accuracy, a clear visual endpoint, and versatility. However, it's essential to be aware of the limitations, including its sensitivity to light and uh, air, the need for fresh solutions, and the influence of the operator skill. By following safety precautions and considering environmental impacts, iodometric titration can be performed effectively and safely. So thank you, if any, thank you for watching this video. Hope you liked it. Thank you.